So here we want to take a look at the circulation and flux form of Greens theorem. As you can see, Greens theorem deals with simply connected plane regions. So we have a simple region if it does not cross over itself. For example, this one is simple, this one is simple, but these are not simple. And again, here are some examples of simply connected. That just means that we can go all the way around and have an area that's enclosed by the curve. Now we'll also require that we have an oriented curve. Now, as you can see, we refer to this as being oriented counterclockwise. That would be our positive direction. And so I put some examples on here. If we're have a region like this first one, then we would be going counterclockwise. And if you put an arrow on here in the direction we're traveling on the curve, the interior region, the simply connected region that we're talking about using in Green's theorem, would be on the left. Now, the circulation form of Green's theorem simply tells us that we can evaluate the line integral f dot t ds around a closed curve by integrating the double integral over the region, which is the derivative of the second component of our vector field with respect to x, minus the derivative of the first component with respect to y. And you might recognize this as being the curl from back in the previous section. So here is how that works. The idea is, instead of integrating this the usual way, which would be to integrate on each line individually, and add all of those up. Or by Green's theorem, we can integrate over the region the qx minus py. So here is the two components of the vector field. X component, our first component, is x to the 4. Second component, x times y. We do the derivative of each of those. And again, we're wanting the derivative of q with respect to x minus the derivative of p with respect to y, which would just be y. Then we need to describe the area of that region. Well, we can describe that by finding the equation of the line and just using x's and y's. We want y to go from 0 to 1 minus x, and then x to go from 0 to 1. And we get the same value. So to evaluate this line integral on the closed curve described as the circle with radius of 3, oriented counterclockwise, here's how we would utilize Green's theorem. Well, we'll take the p and the q from the dx and the dy. That would be our vector field components. We'll do the derivative of those, derivative of p with respect to y, derivative of q with respect to x. So our integrand would be 7 minus 3. Then we want to describe the region. Well, since this is a circle with a radius of 3, the best way of describing that would be using polar coordinates. So we'll introduce the r, dr d theta, let r go from 0 to 3, and theta go from 0 to 2 pi. So that integral comes out to be 36 pi. Now there may be an occasion to use Greens theorem in reverse. So if we have qx minus py come out to be a 1, then the double integral happens to be the area of the region. Now we could come up with any vector field such that qx minus py equals 1 and do the line integral instead of the double integral. Now here is one way in which the derivative of q with respect to x minus the derivative of p with respect to y would be a 1, and that's for the derivative of q with respect to x to be a 1 and the derivative of p with respect to y to be a 0. Now there's others that would work, but this one works, and we can recreate our q and p by integrating those. And so we could use this vector field and evaluate the line integral of just x dy instead of doing the double integral. Now this is what's called the flux form of Greens theorem. Works much the same as the previous one with just a different integrand. Now remember, we're trying to calculate in this time the flux across the curve, which would be f dot n ds. And so the area of the region could be integrated with the integrand composed of the derivative of the first component with respect to x plus the second component with respect to y, which is the divergence. So in this example, we're trying to compute the flux across the curve, which is the circle with the radius of 2, and there's our vector field. So here we'll do the derivative with respect to x on the first component, derivative with respect to y on the second component, and that becomes our integrand. Now again, to describe this region, we would best do it in polar coordinates by letting r go 0 to 2 and theta 0 to 2 pi. So here is the flux integral evaluated using Greens theorem. So here we want to find the flux of the vector field given here across the triangle with vertices at 0, 0, 1, 0, 0, 3, and 0, 0. So here are the P and Q, as we've been calling them. Here's the derivatives with respect to x and y respectively. And so our integrand would be y squared plus x squared. Now to describe the region with those vertices, we'll do that in rectangular coordinates. We'll let our y's go from 0 to the line 3 minus 3x, and then our x's would go from 0 to 1. And again, we can just type that into our calculator. You're not going to have any problems involving this, but you will see this probably in future classes, either physics engineering or differential equations. The idea that we looked at earlier of a conservative vector field can be extended to flux integrals, and we have what we call a source-free vector field, which we call by the Greek letter psi. So that's the potential function for a source-free vector field.